our webinar with our next speaker, Jeff Carmichael, the Director of Marketing at Chroma Technology. Previously, Jeff spent 16 years working in a biomedical research lab at the University of Massachusetts Medical School, becoming very familiar with Chroma's optical interference filters. In 2007, Jeff joined the company as an application scientist and moved into marketing 6 years later. He now leads the company's marketing efforts. Jeff, thanks so much for being part of our webinar today. And Jeff, I see that you too have brought a poll question for our webinar audience. So let's bring that up on screen now. The question is, which of the following machine vision applications do you think is most appropriate for higher quality optical filters? Please select either for routine use, for more demanding but still conventional applications, or for OEM instruments that require custom performance. Please send in your response now. We'll review the results after Jeff's presentation. Jeff?
Thank you, Lisa, and thank all of you who are spending some of your time with us during a busy Thanksgiving week. Today, we'll talk about contrast in images, how optical filters influence contrast in imaging applications, and how this contrast influences the modulation transfer function of an imaging system. Now, garbage in, garbage out is really just meant to get your attention to think about ensuring that the output of the imaging chain is optimized. And that means optimizing the inputs, which is what optical filtration can do. Now, what is the modulation transfer function, and why should we care? First, let's break down the term itself and then just refer to it as MTF to save a lot of words in this presentation. First of all, modulation here simply refers to what we normally think of as contrast. The MTF measures how well the contrast in the object is preserved or transferred as contrast in the image of the object. So it's how well is that contrast transferred from the object to the image. The function part of the term then applies this transfer of contrast as a function of spatial frequency. And together, this measures the practical resolution of your system under the particular test conditions. So we should care because it tells us the practical limits of resolution of a given imaging system or any combination of imaging components. Resolution defines the smallest distance separating two objects that an imaging system can reliably detect. In other words, at what point do they become so close together that the imaging system cannot separate them and they convolve together into one object? That's the resolution. This illustration of line pairs helps us think about this. Each black stripe and a neighboring white stripe on the left make up a line pair, and these line pairs repeat in some pattern. On the bottom half of the slide, we see a higher frequency of the occurrence of these line pairs. They're thinner and spaced together more closely than in the low frequency example above it. The transfer of contrast becomes less efficient as these line pairs become thinner and more tightly packed. The two figures inset at the top of this slide help explain what's going on a little better. Contrast can simply be thought of as the difference in brightness between different features in an object or an image of that object. We intuitively know that high contrast means easily distinguishable light and dark regions paired together, and that low contrast means light and dark regions with little difference, making it more difficult to distinguish them from each other. This figure in the upper left uses grayscale bars to illustrate varying levels of contrast from 100% contrast per line pair down to around 10% contrast. And we say percent contrast because, as we can see from the formula, it's a division. We subtract the minimum intensity value from the maximum intensity value of the features of interest, and we divide that difference by the sum of the same minimum and maximum intensity values. And because we're dividing these values, we'll get a quotient between 1 as the largest possible result and 0 as the smallest. A value of 1 equals 100% contrast and 0 equals 0% contrast, whereas 1/2 equals 50% contrast. The figure on the upper right helps illustrate why all this happens. Because every lens has a characteristic point spread function, or PSF, every imaged point of the infinite number of points in a scene all convolve together when imaged through the lens, each point convolved by the PSF of the lens. So in this case, which is super oversimplified, we can think of the square wave object as one of the lines in a line pair. Each of these infinite number of points that make up that object are imaged through the lens and convolved by its PSF. These convolved points are represented here in this figure by colored sine waves, which superimpose on each other and are summed up into a jumble of blurred points that make up an image, distorting the shape of the object and rounding it towards a sinusoidal shape. And remember that this is an ideal lens that does this. It's physics. It's not bad optics, although bad optics make it even worse. Making this even more challenging is that the summing up of all these sine waves is exacerbated by the fact that the PSF smears each photon according to its own wavelength. So not only is each point imaged, but photons of different wavelengths from each of these same points are imaged and convolved together. However, that's exactly where optical filters can help. Optical filters can't do anything about convolution resulting from the point spread function of a lens, but they can limit the optical complexity caused by a whole array of photons of different wavelengths summing up together on the pixels of the sensor. So here we see the MTF in action. The two images on the upper right were acquired from standard photographic targets printed from the 1951 U.S. Air Force test chart, one with the MV450/20 blue filter and one with no filter. The accompanying histogram on the left plots the points along the yellow line drawn through the line pairs near the top of each image. The obvious thing to notice about the test targets is that the lines are thinner and more crowded together as you move from left to right. This is referred to as spatial frequency, and it's expressed in terms of cycles per millimeter, where one cycle equals one line pair. So one line pair per millimeter equals a frequency of one cycle per millimeter. The bottom row is treated the same, except that the imaged objects were photocopied versions of the targets. This more closely resembles imaging barcodes, which are printed with inks. These inks have varying spectral reflectance, and the printed patterns have varying levels of smear or smudging, making resolution more difficult than with the standard targets. The illumination used to acquire all of the images was broad white light from an incandescent source, intended to provide a broad array of wavelengths, including what might be considered ambient lighting conditions in a factory floor setting, or sunlight streaming through shop windows. Each of these objects was imaged in 4 conditions: no filter on the lens, or either with a red, a green, or a blue filter on the lens. So each histogram has 4 plots, but because of time constraints, we'll just look at data from 2 of these, the no filter and the blue filter conditions. What's immediately noticeable in the top histogram is that the blue trace, which is the image data of the blue filtered image, has noticeably lower black levels from the black lines than the other images across the entire range of spatial frequencies. And the white levels are higher as frequencies become greater. The data in the bottom histogram similarly show a much improved range, which we'll quantify in the following slide. And I want to point out that the imaging was performed and provided by Smart Vision Lights, and we're very grateful for their collaboration. So this is the result of our testing. This is the classic way to visualize an MTF, and it's familiar to many of you experienced with inspecting the MTF of imaging lenses. The main differences are related to the spectral distribution of the light detected by the sensor. A broad white light source was used, but in the case of the images filtered with the 450/20 filter, this range is dramatically reduced all the way down to 440 to 460 nanometers. This is what we would normally call indigo as a color. This is a dramatic increase in MTF for both conditions. Surprisingly, use of the blue filter improved the MTF of images of the standard target even more so than the images of the photocopied target, especially in the ranges of 1.5 to 2 cycles per millimeter. I see 3 takeaways from this data. 1, even with what seem like easily discernible high contrast features in an object, filters always help even when the contrast is already relatively high. And 2, in these situations where good contrast is present, when you move into the realm of higher spatial frequencies, this is where filters can provide a more dramatic improvement. And 3, when imaging things like barcodes, an average increase of between 20 and 25% contrast at all spatial frequencies is extremely valuable. And given that we've demonstrated this with approximately 450 nanometer light, strobing a commonly available 450 nanometer LED at ultra-fast speeds in combination with a filter such as this filter can dramatically increase throughput and also minimize bad reads. This dramatic improvement is not achieved with just any filter that happens to span these wavelengths. As the following slides will illustrate, an accurate and precisely reproducible passband shape is critical to achieving this improvement. Here we see a different wavelength range used to improve contrast. Here are 2 green filters, the top one centered at approximately 525 nanometers and the bottom filter centered at approximately 530 nanometers. The real difference is that the interference on the top is manufactured by sputter coating the thin films onto a single very simple short pass thin film coating applied. Also, notice the obvious difference in passband shape. The top sputter-coated filter plots a square wave transmission profile, whereas the colored filter on the bottom plots an irregular Gaussian transmission profile. Then note the difference in real measured contrast when imaging the Lego bricks pictured on the left. Color in this case isn't just a gimmick. Although Lego bricks are easily recognizable colored objects, most everyday real-world objects have color. We don't live in a black and white world, even though most image sensors used in machine vision are monochrome sensors. Color is a real everyday component of contrast. And notice the difference in levels of contrast is in the red and green levels, which should be really easily discernible differences in contrast, increase in this case from 49 to 65%. And the difficult to measure difference between the red and purple almost double from 18 to 35% contrast. That means that objects that are below a reliable contrast threshold in machine vision become easily differentiated with a sputter-coated square wave filter. Finally, consider that these particular images were acquired with an RGB ring light with output of all 3 LEDs balanced to a white light source. It's not just a green light. The sputter-coated interference filters do all of the work, allowing the use of any light source. So in other words, the filter allows the use of a white light to create the same level of contrast as any colored light. Now, what is a sputter-coated interference filter? We don't have the time to go into this in depth today, but briefly, reactive magnetron sputter coating is a process where highly energetic ions bombard pure targets of alternating high and low index of refraction materials, such as a metal and a silicon, in an alternating manner back and forth, programmed to create precise thicknesses of each thin film layer. And there are typically hundreds of layers. These coatings are dense, they're uniform and durable, very high in transmission, and very high in optical density in the out-of-band regions where blocking of unwanted light is required. Now here we see a red 630 nanometer LED and its spectral output superimposed by this orange plot of a square wave sputter-coated red filter. also centered at 630 nanometers. And finally, a Gaussian-shaped colored glass filter with the same 630 nanometer center wavelength. Note that the square wave filter only contains those wavelengths from the LED output, whereas the colored glass filter also transmits light outside this range. Now, some of you may have read the myth that Gaussian-shaped filters are better suited to transmit the light from LEDs with a Gaussian-shaped output distribution. As standard signal processing techniques easily demonstrate, this is not the case. If certain wavelength ranges are desired, square wave transmission profiles will always more accurately transmit the desired wavelengths and block the undesired wavelengths. And here's the math. I'm using a basic optical signal processing formula for signal-to-noise ratio using the previous slide as the example. Here we've measured each filter in the same spectrophotometer and plotted the transmittance, which includes both transmission and optical density. What we're measuring here is how effectively each filter transmits this red LED spectra and blocks unwanted wavelengths outside the passband, and then calculates a signal-to-noise ratio for each filter. I've included a random background ambient light level. It's the gray shaded region on the bottom. I chose a level of background light that is broad spectrum and equal to about 10% of the peak intensity of the red LED. This is a simple integration where we multiply the area under the curve of each filter in turn by the area under the curve of the LED output. Then subtract what we've defined as noise and divide this difference by the square root of the noise. It's a basic optical signal-to-noise ratio. I've provided two examples, one conservative case, number one, where all ambient light, even that which is coincident with the desired passband, is considered noise, and one where only the ambient light outside of the passband is considered noise. In this first conservative case, we see a 20% increase in signal-to-noise ratio, and this assumes all ambient light is bad, such as when dark field lighting is employed. In that case, any random multi-directional ambient light is bad. In the second case, I've assumed that any light within the desired passband is helpful and only the light outside the passband is harmful. In this case, the increase in signal-to-noise ratio is almost 25-fold, or almost 2,500%. So accuracy in this sense means transmission band shape and also out-of-band blocking, and is a key consideration when choosing filters for imaging applications. The aspect of transmittance that we haven't really addressed is blocking, or out-of-band optical density. This graph plots the transmission and optical density of both these red filters as measured on a high-performance spectrophotometer. The x-axis denotes wavelength, while the two different y-axes measure transmission on the left and optical density on the right. By convention, when transmittance levels fall below 1% transmission and are too small to see on the linear %t plot, we plot them logarithmically and refer to them as OD values, labeled on the right side axis. The shaded plots are the transmission plots we've already seen, while the solid lines outside of the passbands plot the OD levels. Note the dramatic difference in both the level of OD and the steepness of the lines in transitioning to a high level of OD. The areas under the curves where OD is relatively low represent areas where noise is introduced into the image, degrading the signal-to-noise ratio. Another key consideration for filters is precision. Precision means reproducibility. Regarding filters, this means always the same wavelength ranges with tight tolerances so that you can count on the exact same performance every time. Sputter-coated interference filters provide this level of precision. This graph plots the spectral output distribution of a blue LED centered at 450 nanometers. This next graph plots the same MV45020 blue filter that we used in our MTF determination earlier. This is a real measured transmission spectra of a production lot. And here we have a second independent production lot of the same filter, and a third, and a fourth, and a fifth, and a sixth, and a seventh, eighth, ninth, and so on. So you get the point. Reproducible, same wavelengths every time. The third characteristic to consider when choosing optical filters for imaging applications is the bandpass. It's the obvious one. Here I've illustrated common RGB LEDs with corresponding filters that match the peak wavelength of the LEDs. In each case, a thick red trace denotes a very narrow 10 nanometer wide filter, a green trace is a 20 nanometer wide filter, and the thin blue traces are 40 nanometer wide filters. Which filter you choose depends on empirical testing of the application, easily done with a white light source. Once you determine the most effective filter, then choose the corresponding LED. The two images on the left are also courtesy of Smart Vision lights. The barcode image in the upper left shows a clean barcode and a bad read with a motion blur. The image below it depicts the pulse widths of 3 light sources. The black trace is a xenon flash lamp. The red trace is a conventional LED with an external controller, and the blue trace of a next generation LED with an integrated driver and controller, and exceedingly fast rise and fall times of less than 500 nanoseconds. The blue trace has an entire pulse width of less than 1.5 microseconds. Which would you choose for your barcode reading application? And when paired with the empirically determined filter, you'd be on the way to faster and more accurate barcode reading. So these 3 characteristics are what influence the best choice of an optical filter for a machine vision application. Another myth that is OD values greater than 3 are unnecessary in MV applications. While this may be true for many applications, it certainly doesn't apply to many other applications which can benefit from higher levels of optical density. This slide illustrates how the increase of optical density of sputter-coated interference filters outperforms colored filter glass filters. Notice the level of blocking, or OD, of the red laser pointer. In this case, looking at the same filter as the signal-to-noise ratio calculation that we looked at earlier, the sputter-coated interference filter provides several orders of magnitude greater out-of-band blocking compared with the colored glass filter. These applications in this next slide will all benefit from the more extended levels of blocking that sputter-coated interference filters provide, including protection from direct sunlight and lasers used in industrial laser-guided machining. Finally, the myth of high angle of incidence causing interference filters to fail. Interference filters can be designed to accommodate high angle of incidence. Getting around that problem, all we have to know is that your application requires high angle of incidence. This slide illustrates the acquisition of images with a wide-angle lens, and you can see the barrel distortion in each image indicative of a wide-angle lens. In this case, the sputter-coated interference filter does no worse at the region of interest near the edge of the image versus the colored glass filter. So, filters improve contrast, to summarize, which improves MTF, which is important for designing the simplest, the most cost-effective, and the most reliable vision systems. Thank you very much for your time. And here's a contact slide if you want to get in touch with us for a custom-designed filter to suit your application. Thank you, Lisa.
Wonderful presentation. Thank you, Jeff. Let's bring up on screen now the results of the poll question that we asked before your presentation. The question was, which of the following machine vision applications do you think is most appropriate for higher quality optical filters? And as we can see, there is a tie. About a quarter of our audience said for routine use, but the rest of the audience is split between for more demanding but still conventional applications and for OEM instruments that require custom performance. Jeff, what do you think of the audience's response?
Can you? I'm sorry, I was having audio difficulties. Can you repeat the numbers?
Oh yes, about a quarter of our audience selected for routine use, and then the rest is split, about 37% each for more demanding but still conventional applications, and for OEM instruments that require custom performance. So there's a tie between the last two answers.
Honestly, that's a little bit encouraging to me because often what we encounter is folks are pretty used to and familiar with the traditional colored glass filters, and I get the sense that most people tend to think that's sufficient and that's all that's needed. So part of this talk was to try to demonstrate that even with relatively straightforward applications like reading a line chart, that high performance filters can make a big difference. So that's actually encouraging to me.
Oh, that's good news. Wonderful. Thank you, Jeff. And thanks to everyone today in our webinar audience who answered our poll questions for us. Now, before we begin our Q&A, I also want to thank today's sponsors for making this webinar possible: Chroma Technology, Nikon Metrology, RPMC Lasers, and Teledyne DALSA. You may download PDFs of sponsor technical papers by clicking the links under Event Resources on your screen. Here you will also find PDFs of our speakers' slides. And now let's begin our Q&A. Please send in your questions through the Ask a Question box, and our first question is for Brad. Brad, can your scan head be used or integrated with current systems we have in use? Brad?
So it's an excellent question. So can you adapt these scan heads on the current technology you have? And many vendors out there have applications that can be adapted to existing equipment. So the real way to answer that would be to contact your local manufacturer. Certainly if you go out there, but there are many opportunities to upgrade non-contact sensors on existing equipment. So I would encourage you to go out and do some research on the existing equipment or look out into the market. There's a number of different solutions available.
Very good. Thanks, Brad. Jeff, this question is for you. You mentioned that you can use a broad white light source for these filters. Why do you say this when we're generally taught that you should avoid this and use colored LEDs? Jeff?
So there's a couple answers to that question. One of them is it's pretty much just historical that many years ago, red LEDs, since they were relatively cheap and safe to make, came into vogue. And since any colored LED, a red LED will limit wavelengths. This was before filtration was used very much. That was the way of limiting the spectral range in an image, was simply with the LED. The reason I say a white light is fine to use, I'm not necessarily suggesting that in imaging applications on the floor where fast imaging is required that you use a white light, although it would be perfectly fine. The filter does all of the filtration work. You don't need to limit the wavelengths you're illuminating an object with in order to limit the wavelengths the camera sees. The filter does that far better. Now, in applications requiring high speed or really high output, and you're using a filter, you're probably going to want to pair that with an LED that can strobe or overdrive and put out a lot more light over a 20 nanometer range than you could squeeze out of a white light. But when doing testing, and you haven't put the system together yet, use a white light, because then you can you can test every possible wavelength range. And then at the end, you've optimized the range and you can pick the LED.
Yes, thank you for that advice. Brad, someone in our audience wants to know, do you have applications in mining environments?
Yeah, that's actually a very interesting question, and there non-contact sensors have been used in some different mining applications, especially in areas where for large pieces of equipment have been digging tunnels, as an example, and there may be a target on the back of the equipment that's actually being used to drill in these areas, and it's actually the sensor is on that piece of equipment to ensure that it's in line, it's traveling where it is. Or a non-contact sensor could be used if you were thinking about large-scale inspection to confirm that the correct construction is being done, to verify that the right beams or support mechanisms are in place. So there are applications. It certainly isn't on one of the major industries that I had mentioned during my talk, but certainly there are applications for non-contact sensors in various mining applications.
Very good. Thank you, Brad. Jeff, this question asks you, it says, you're suggesting that we do some testing, but how do you know which filters to choose? Interesting question. Jeff?
Yeah, so this is a little bit related to the previous question that I answered. If you use a white light source, like a broad white LED, you often don't have much information to know where to start in order to choose a wavelength range to improve the contrast in your image. Sometimes you do because you've done something similar before and you know roughly where to look. Even in that case, let's say you've decided blue light is what you need. Which blue light? How wide a bandpass is probably even more important. How much of the ambient light is present that you need to block out? How narrow is the spectral output of that LED? That helps guide how wide the bandpass should be. And when you don't really have much guidance, it allows you to use something like a filter kit that has a broad selection of filters and just empirically play with it. Just take filters out and trial and error, take images and see which ones actually improve contrast of the feature of interest.
Excellent. Thank you, Jeff. And with that, we're at the end of our webinar. I want to thank both Brad and Jeff for this discussion today. I also want to thank our audience for being with us. A survey will pop up on everyone's screen immediately following our program. Please tell us what you thought of our webinar by answering just 3 questions. This webinar will be archived and available for viewing on our website. An email will be sent to everyone who registered for today's program as soon as the archive is ready. Once again, thanks for joining us.